morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here.
It is wonderful to be back.
This is Andrew and Renee. Welcome to the Stack series.
Happy to be here.
Today, we are exploring something that I think a lot of us take for granted, but the more you think about it, the weirder it gets. We're talking about the unreasonable effectiveness of mathematics.
And just as importantly, its occasional and sometimes catastrophic ineffectiveness.
Exactly. I was thinking about this the other day. It feels like magic, doesn't it? We can sit here in a room and just scribble some symbols on a piece of paper.
Right. Just abstract thoughts.
Just abstract thoughts. And those squiggles can tell us with perfect accuracy where a planet will be in 100 years. They can predict the existence of something like the Higgs boson decades before we could ever build a machine powerful enough to find it.
It's like we found the universe's source code, or at least a part of it. There's this feeling that the fundamental structure of reality is somehow mathematical. It's a kind of magic spell. But then, and this is the twist we want to explore, sometimes the spell just completely backfires.
It really did.
We use it, and instead of revealing a hidden truth about the universe, it hallucinates something that isn't there. Or it fails to capture the messy, complicated reality of, life.
And that's the central tension for our conversation today. We're drawing on the work of people like Eugene Wigner, who coined that famous phrase, the unreasonable effectiveness of mathematics. He called it a miracle.
A miracle we don't deserve, I think he said.
He did. But we're also looking at thinkers like R.W. Hamming, who asked a more skeptical question. Is it really a miracle, or are we just looking at the world through math-colored glasses?
So we're going to explore all of it, where the map perfectly matches the territory, where the map is just plain wrong, and maybe most importantly, where confusing the map for the territory can lead to absolute disaster.
We have a lot to get through. Everything from philosophy to a brand new paper on Mercury's orbit that, it pokes a few holes in some very established science.
And then we'll get to the real-world consequences in biology and economics. It should be quite a journey.
Let's get started.
So let's begin with part one, foundations, what we think we know. This is the core idea, the Pythagorean dream, as some call it, the belief that all is number.
Yes, this ancient intuition that the universe isn't chaotic, that it has an underlying order, a logic, and that this logic somehow mirrors the logic in our own minds.
But the mathematician R.W. Hamming, he really threw some cold water on that, didn't he? He came up with this idea of selection bias.
He did, and it's a profound challenge. Hamming essentially says, wait a second, is math so effective because it describes the universe perfectly? Or is it that we only choose to study the parts of the universe that our mathematical tools can handle?
So it's the old joke about the person looking for their keys under the streetlight, not because they lost them there, but because that's where the light is.
That is the perfect analogy. We have this wonderful tool, mathematics, and we go around looking for problems it can solve. We find them, things like gravity, electromagnetism, and we say, wow, look how mathematical the world is.
But we're completely ignoring everything that's still in the dark.
Precisely. Hamming's own analogy for this is just brilliant. He asks you to imagine some scientists who go fishing in the sea with a very particular net.
Okay.
They cast this net thousands of times, and every time they pull it up, they examine their catch. After years of research, they publish a fundamental law of marine biology.
Which is?
There are no fish in the sea smaller than 2 inches.
But of course there are. They just swam right through the holes in the net.
Exactly. The net is our mathematics. We catch the problems that fit its structure, and we conclude that the entire sea of reality must have that same structure. We might be letting vast domains of reality consciousness, aesthetics, social dynamics slip right through the mesh.
That's a really humbling idea. Our greatest intellectual achievement might just be a reflection of our own limitations.
It could be. Hamming also had this evolutionary argument that I find compelling. He said our brains didn't evolve for discovering ultimate truth.
No, they evolved to keep us from being eaten by tigers.
Right, to help us throw a spear and hit a moving target, or to figure out if we have enough food for the winter. Our brains are optimized for survival in a world of medium-sized objects moving at medium speeds.
Not for quantum mechanics or general relativity?
No. So the math we naturally developed, like basic arithmetic and Euclidean geometry, is, in his view, a form of lossy compression. It's a simplified model of reality that throws away all the messy details we don't need just so we can make quick life-or-death decisions.
But then we make the mistake of assuming that compressed file is the original high-resolution image of the universe.
That's the danger. And you can see the cracks appear when you push that math to its absolute limits. Which brings us, I think, to one of the weirdest ideas in all of science.
You must be talking about the Banach-Tarski paradox.
The ultimate mathematical party trick.
It sounds like a joke when you first hear it, so let's just lay it out for everyone. You take a solid ball. Let's say a solid gold sphere.
Okay, a gold sphere.
The theorem states that you can cut this ball into a finite number of pieces. I think the record is 5, right?
As few as 5, yes. But they are very, very strange pieces.
Incredibly strange. So you cut it into these 5 pieces. You don't stretch them, you don't bend them, you don't add any new gold. You just move them around, you rotate them and translate them.
Purely rigid motions.
And when you're done, you reassemble them, and you now have 2 solid gold spheres, each one identical in size, volume, and weight to the original one you started with.
You have, mathematically speaking, created matter from nothing. One has become 2.
Now, obviously, we can't do this.
Yeah.
If we could, the global economy would look very different. So what's going on? Why does a proven mathematical theorem describe something that is so obviously physically impossible?
This is the first major crack in the mirror between math and reality. The paradox hinges on what you mean by pieces. When the theorem says cut, it doesn't mean with a knife.
Okay.
A physical object, like a gold sphere, is made of atoms. It's discrete. But a mathematical sphere is a conceptual object. It's an infinite collection of dimensionless points.
An infinitely smooth continuum.
Exactly. The cuts in Banach-Tarski are not physical cuts. They're abstract divisions that create something called non-measurable sets.
Non-measurable, so you can't assign a volume to them. You can't say, this piece is 1 cubic centimeter.
You can't. Imagine trying to cut a cloud of dust. The pieces are so infinitely fine and scattered, so porous and fractal-like, that the very concept of volume breaks down. They're like geometric ghosts.
So the math is exploiting the concept of infinity.
It is. It relies on a foundational rule of set theory called the axiom of choice, which lets you perform these infinite selections. The math assumes you can divide matter an infinite number of times.
But reality doesn't let you do that.
Reality puts up a stop sign. You can cut a gold bar in half, and then half again, but eventually you get to a single gold atom. You can't cut that atom with a knife and still have gold. You hit a fundamental limit.
You hit a pixel. The world is pixelated.
That is the perfect way to put it. The map of mathematics describes a smooth, continuous world. But the territory of physical reality is granular, it's discrete, it's made of quanta atoms, photons, Planck lengths.
So Banach-Tarski isn't a paradox in physics. It's a warning from math that its rules don't always apply to our world.
It's a beautiful demonstration of the boundary. It shows that mathematical truth and physical truth are not the same thing. And that distinction is crucial because sometimes when the math and the world disagree, we get so confident in the math that we try to change the world to fit it.
Which seems like a good transition to our next section, active debate, where science disagrees. And there's no better story for this than the hunt for the planet Vulcan.
Oh, this is one of the great cautionary tales in science.
It's a story about the danger of success. In the mid-19th century, Newtonian physics it was everything. It was the law. And its greatest champion was the French astronomer Urbain Le Verrier.
An absolute rock star of his day. And for good reason. He had looked at the orbit of Uranus, which was wobbling a bit. It wasn't quite where Newton's laws said it should be.
Right.
So Le Verrier sits down, does the math, and he predicts that the wobble is being caused by another unseen planet. He even calculates exactly where it should be in the sky.
He sends a letter to an observatory in Berlin. They point their telescope where he said to look, and bam, they find Neptune.
Instantly. It was maybe the greatest triumph of theoretical physics up to that point. It proved that Newton's math wasn't just descriptive, it was predictive. You could use it to find new things in the universe just by trusting the equations.
So with that incredible success under his belt, Le Verrier turns his attention to the other problem child of the solar system, Mercury.
Yes, Mercury's orbit was also off. Specifically, its perihelion, the point where it's closest to the sun, was shifting or precessing a little bit more than the maths predicted.
And we're talking about a tiny, tiny amount, right?
Incredibly small. After you account for the gravitational pull of all the other known planets, like Venus and Jupiter, there was a discrepancy of just 43 arcseconds per century.
To give people a sense of scale, an arcsecond is 1/3600th of a degree. So this is a minuscule error.
It's a hair's width. But in the perfect clockwork universe of Newtonian mechanics, it might as well have been a cosmic train wreck. It meant the law was broken.
So Leverrier, high on his success with Neptune, does the exact same thing again. He says, the math isn't wrong. There must be an unseen planet inside Mercury's orbit, tugging on it.
And he even names it. He calls it Vulcan, after the Roman god of the forge.
And because he was Leverrier, the man who found Neptune with a pen, everyone believed him. Astronomers around the world started hunting for Vulcan. People even claimed to have seen it.
For decades, they'd see a sunspot and telegraph Leverrier, claiming they'd found his planet. The desire for the math to be right was so powerful that they literally started hallucinating a planet that didn't exist.
Of course, Vulcan was never found. The solution had to wait until 1915.
For Albert Einstein, he came along with his theory of general relativity and said, the problem isn't a missing planet. The problem is that Newton's theory of gravity is wrong, or at least incomplete.
Gravity isn't a force pulling things, it's the shape of space-time itself.
Exactly. The sun is so massive that it creates a deep curve, a well, in space-time. Mercury is orbiting so close and so fast that it's affected by that curvature in a way the other planets aren't. When Einstein ran the numbers for Mercury's orbit using his new equations,
the missing 43 arc seconds popped out perfectly, no Vulcan needed.
And that's the story we all learn in school. Newton was a good approximation, but Einstein revealed the deeper truth. The map was updated. Case closed.
But as part of this exploration, we found a fascinating and very recent paper that suggests the case might not be as closed as we think.
Yes, this is where the active debate really comes in. It's a 2024 paper by a physicist named Christian Korda, and it offers a really provocative alternative. He's not saying Einstein is wrong, but he is arguing that we might have dismissed Newton a bit too quickly.
How so? How can you possibly explain Mercury with Newtonian physics?
Well, Korda argues that the original Newtonian calculations made a subtle but critical error in their assumptions. They treated the sun as a perfect, stationary anchor, what physicists call an inertial frame of reference.
But the sun isn't stationary. It gets pulled on by Jupiter and the other planets, so it wobbles.
It wobbles. It's a non-inertial frame. Now, astronomers knew this, but Korda's insight is to combine this fact with a key piece of physics that came after Newton but before full general relativity: time dilation.
Okay, so time moving at different speeds.
Right. We know from relativity that time flows slower in a stronger gravitational field. A clock on the surface of the sun would tick more slowly than a clock out here on Earth or a clock near Mercury.
This is the thing from the movie Interstellar.
It's exactly that. Korda's big idea is this: what if you use Newton's laws of motion, but you account for the fact that time itself is being warped by the sun's gravity and rotation?
So you're putting a relativistic concept, time dilation, into a Newtonian framework.
Precisely. You're giving Newton an upgrade. Think about it. A planet's velocity is distance divided by time. If the time part of that equation is variable, if it changes depending on how close you are to the sun, then your whole calculation of the orbit is going to change.
So the original Newtonian model was using a single universal clock for the whole solar system.
Yes, it assumed time was absolute. Korda recalculates Mercury's orbit using Newton's laws, but corrects for both gravitational time dilation and the time dilation caused by the sun's own rotation. And when he does,
He gets the 43 arc seconds.
he gets 42.98 arc seconds per century, the exact number.
Wow. So
Yeah.
he doesn't need curved spacetime at all.
According to this paper, no. He gets the right answer just by using Newton's laws in a non-inertial frame and adding the physical reality of time dilation. It suggests there's this intermediate framework between Newton and Einstein.
It really blurs the lines. It's not that Newton was wrong and Einstein was right, but that Newton's model was more powerful than we realized. It just needed more accurate inputs.
It's a powerful reminder that the history of science isn't a clean line of progress. It's messy, and old ideas can sometimes come back in surprising new ways.
And this wasn't the only time classical physics predicted something completely absurd. We have to talk about the ultraviolet catastrophe.
Yes, another case where the math predicted infinity and nature just said no.
So set this up for us. In the late 19th century, physicists were trying to understand a seemingly simple problem: black body radiation.
Which is just a fancy term for how things glow when they get hot. A hot poker in a fire, the filament in a light bulb. A black body is a theoretical, perfect absorber and emitter of radiation.
And the math they had at the time, the Rayleigh-Jeans law, worked beautifully for low-energy, long wavelengths, like infrared radiation. The model matched the experimental data perfectly.
It did. But the problem started when they pushed the math to higher energy, shorter wavelengths, moving up the spectrum toward visible light and then into the ultraviolet.
And the graph just went vertical.
It went to infinity. The law predicted that a hot object should radiate an infinite amount of energy as the wavelengths get shorter and shorter.
Which, if true, would mean that turning on a toaster would be a very bad idea.
It would be an extinction-level event. Opening your oven door would flood the universe with a lethal infinite blast of UV rays, X-rays, and gamma rays. Everything would be instantly vaporized.
But obviously that doesn't happen. My toast is safe.
Thankfully, yes. Reality refused to obey the math. The experimental data showed that the energy emission peaks in the visible spectrum and then drops off sharply in the ultraviolet. The math predicted a catastrophe, but reality was well behaved.
And this failure, this breakdown of the model, is what led to the birth of quantum mechanics.
It's the whole reason it started. Max Planck was staring at this problem and realized the only way to fix the math was to make a radical assumption. He proposed that energy isn't emitted smoothly, like a continuous stream of water.
But in discrete little packets.
Little packets he called quanta. And with that one simple revolutionary idea, he fixed the equation, resolved the catastrophe, and accidentally invented a whole new field of physics.
So here we see that same theme again. The classical math assumed a smooth continuum, but reality turned out to be grainy, to be quantized.
It's the same lesson as Banach-Tarski, but for energy instead of matter. Whenever a model predicts a singularity in infinity, it's usually a sign that nature is trying to tell you that your theory is broken and you need a new idea.
Okay, so math works pretty well in physics as long as we pay attention when it screams infinity at us. But now let's move into the frontiers, because when we try to apply these same tools to biology and culture, the effectiveness starts to seem a lot more reasonable.
Or even, as one of our sources puts it, the reasonable ineffectiveness of mathematics in the biological sciences.
That's a direct shot at Wigner's famous phrase. What's the core argument here?
The core argument from that paper by Marshall and his colleagues revolves around a concept called algorithmic compressibility.
Okay, let's break that down.
In physics, you can often take a huge, complex system and compress all of its behavior down into a single, elegant equation. Think about Newton's law of universal gravitation. That one little formula describes the motion of apples, moons, and galaxies. It's an immense compression of information.
You can write the rules for the whole solar system on a napkin.
Exactly. The argument is that biology fundamentally resists this kind of compression. You can't write down a simple set of equations that describes the behavior of a bacterium, let alone an ecosystem.
And why not? Is it just because it's more complicated?
It's more than just complexity. It's because living systems have something that rocks and planets don't: agency.
Agency. You mean they make choices, a single cell?
In a meaningful way, yes. Think about the difference between a computer and a cell. A computer, or a Turing machine, is the perfect example of a system that follows mathematical rules. It has a tape with a set of instructions, a program, and it executes that program blindly. If you know the program and the input, you can predict the output with 100% certainty.
It's deterministic.
Completely. A biological cell is not like that. A cell can, in response to its environment, effectively rewrite its own tape. It can change its own program.
So it's not just running code, it's actively debugging and rewriting its own code in real time.
Yes. Faced with a new toxin or a shortage of food, a cell can rearrange its genome, activate dormant genes, and essentially innovate new solutions. It explores what the biologist Stuart Kauffman calls the adjacent possible, the space of things it could become.
Which means if I write an equation to model a cell's behavior today, that equation might be obsolete tomorrow because the cell has changed its own internal rules.
That's the fundamental problem. Mathematics is brilliant for describing systems with fixed universal laws. But evolution is the process of constantly changing the rules in order to survive.
That's why there's no Newton's law of the fox.
There isn't.
Oh.
You can use physics to model the trajectory of a fox jumping, but you can't use an equation to predict its decision to jump in the first place. We're trying to force life, which is historical and contingent, into the framework of physics, which is timeless and universal.
And this problem of agency and unpredictability just gets exponentially worse when you scale it up from a single cell to, say, 7 billion humans. Which brings us to modeling cultural evolution.
This is the absolute frontier. People in fields like social physics are trying to see if we can model human society with the same rigor we model a gas or a fluid. Can we predict a protest or a fashion trend or a viral tweet?
And what are the tools they're using? According to a paper we have by Frederick Jansen, they're borrowing a lot from physics and biology.
They are. They're using things like Bayesian inference to model how people update their beliefs when they get new information. They use game theory to model cooperation and conflict. and social network analysis to see how the structure of who you know affects what you know.
Treating people like particles in a system.
Essentially, yes. If you're a particle connected to other particles that are spin-up, maybe you're more likely to flip to spin up yourself. But as you said earlier, particles don't have fear of missing out.
Right, and Jansen gives a great example of this, the restaurant problem.
It's a classic illustration of herd behavior.
Let's walk through it. You're new in town, you're hungry, and you walk down a street with two restaurants side by side. You don't know anything about them. Restaurant A is completely empty. Restaurant B has a long line of people waiting outside.
Which one do you choose?
I'm going to Restaurant B. I assume the line means the food is good. I'm using the crowd as a source of information.
That's called social proof.
Yeah.
You're assuming the people in line have some private information that the food is great, and you're copying their choice. But now, let's rewind. How did the line start? Imagine the very first two customers that day arrived at the same time. They had no information either, so they just chose Restaurant B at random. A coin flip.
Okay.
Now the third customer arrives. They see 2 people at Restaurant B and 0 at Restaurant A. So they think, oh, B must be better, and they join the line. The fourth customer sees 3 people, and the choice becomes even more obvious.
And then I show up, see a huge line, and I join the herd, reinforcing the signal.
Exactly. You've created what's called an information cascade. The entire popularity of Restaurant B could be based on nothing more than a single random choice at the very beginning. Restaurant A might actually have much better food, but it never gets a chance.
That is deeply unsettling when you apply it to bigger things.
Think about the stock market. A stock starts to go up for no real reason. People see it rising. They pile in, assuming others know something they don't, and you get a bubble based on pure social momentum.
Or a political movement, or the spread of misinformation. A piece of fake news can go viral not because it's true, but simply because a lot of people are sharing it.
And this is what makes cultural dynamics so hard to predict. These systems have tipping points. A society can look stable for decades, with everyone eating at Restaurant B. Then one tiny event, a key influencer tries Restaurant A and tweets about it, and the entire system can catastrophically flip in a matter of days.
It's mathematically chaotic. It's sensitive to these tiny initial conditions that are impossible to measure.
Right. We can model the mechanism of social copying, but predicting the outcome is a fool's errand. We can't see the internal mental states of millions of agents.
And that leads us to the final, and I think most critical part of our analysis today. The implications, particularly when we ignore these limitations and apply physics math to complex human systems like the economy.
This is where the map being wrong isn't just an academic curiosity. It's where people lose their homes and their livelihoods.
We're talking about what some call physics envy.
Yes, this deep desire among economists and social scientists to make their fields as predictive and rigorous as physics. They want elegant laws, they want equilibrium models, they want certainty.
But humans aren't predictable atoms, and the 2008 financial crisis is the ultimate devastating example of this mistake. We have to talk about the Gaussian copula function.
The formula that killed Wall Street?
It sounds so technical, but the idea was simple, wasn't it? It was a mathematical tool designed to measure the risk of these complex financial products, these mortgage-backed securities.
Right. Banks were bundling thousands of individual mortgages together into a single package and selling it as an investment. The copula was supposed to tell them the probability that all those homeowners would default on their loans at the same time.
And the model said that probability was basically 0.
Infinitesimally small. The odds of a total collapse were calculated to be something that would happen once in the lifetime of the universe. It allowed them to take these bundles of risky subprime loans and get them stamped with a AAA safety rating.
So what was the flaw? Why was the math so catastrophically wrong?
The model was mathematically brilliant, but it was built on one fatal assumption. It assumed that individual mortgage defaults were largely independent events.
Like coin flips.
Exactly. The model treated the financial system like this. If you default on your mortgage in Arizona, that's just your bad luck. Doesn't really make it any more likely that I'll default on my mortgage in Florida. The events are uncorrelated.
Which seems reasonable in normal times.
In normal times, sure. But the model completely failed to account for systemic risk. The analogy I like to use is this. Imagine you're trying to model the health of 100 people in a room. The model might assume that if one person gets sick, it's an independent event.
But what if everyone ate the same bad potato salad?
Now everyone gets sick at the same time. The illnesses are suddenly 100% correlated. The housing market was the bad potato salad. When housing prices started to fall, they didn't just fall in one city, they fell everywhere. Panic became the correlating factor.
So the map, the Gaussian copula, said all these risks are separate and contained. But the territory, the real world, said you are all connected in one fragile system.
And the system blew up. It's a tragic case of mistaking mathematical elegance for truth about human behavior.
And if that wasn't bad enough, after the crash, we had another mathematical failure that had massive real-world consequences. The Reinhardt-Rogoff paper.
The spreadsheet of doom. This one is, in some ways, even more infuriating because it wasn't a complex theoretical error. It was a typo.
So in 2010, two very respected Harvard economists, Carmen Reinhardt and Kenneth Rogoff, published a paper called Growth in a Time of Debt. And it had a bombshell conclusion.
It did. They claimed to have analyzed centuries of data and found a hard rule. Once a country's national debt goes above 90% of its GDP, its economic growth collapses. It doesn't just slow down, it turns negative, shrinking by an average of 0.1%.
And this 90% figure became a global obsession. It was the magic number. Politicians all over the world, in the US, in the UK, across Europe, seized on this paper.
They used it as the intellectual justification for austerity. They said, look, the Harvard math proves it. We have to slash spending on healthcare, on education, on social programs, or our economies will die.
It fueled policy decisions that affected hundreds of millions of people, until a graduate student at the University of Massachusetts Amherst tried to replicate their work.
Thomas Herndon. He was given their paper as a class assignment. He tried to run the same numbers, but he kept getting a different result. He couldn't find the 90% cliff.
So he thought he must be doing something wrong.
He did. But after checking his work again and again, he eventually emailed the authors, and to their credit, they sent him their original Excel spreadsheet.
And he found a mistake.
He found several, but the most famous one was a simple Excel coding error. In one of their key calculations, they meant to average the data from 20 countries. They had typed SUM L30.L49 when they should have typed SUM L30.L54.
They just failed to select the last 5 rows of data.
They accidentally left out Australia, Austria, Belgium, Canada, and Denmark from the final average.
And what was special about those countries?
They were all countries that had experienced periods of high debt and solid economic growth. By accidentally deleting the counterexamples, their result was skewed to make high debt look far more damaging than it actually was.
So what happened when he fixed the typo?
The cliff vanished. When the data was calculated correctly, the average growth for countries with debt over 90% wasn't negative 0.1%. It was a positive 2.2%. Slower, perhaps, but not a catastrophe. There was no cliff.
A global policy of austerity, which caused real suffering, was based, in part, on a spreadsheet error.
It's the ultimate example of the map is not the territory. In this case, the map was just smudged, and we drove the global economy based on that smudge. It's a profound lesson in the responsibility that comes with creating mathematical models of the world.
So after all this, where does it leave us? Math seems to be this double-edged sword. It can give us relativity, but it can also give us the 2008 crash.
I think it leaves us needing a dose of philosophical humility, and that brings us to Kurt Gödel.
The man who proved that math itself has limits.
In a way, yes. In 1931, Gödel published his incompleteness theorems, which are among the most profound intellectual achievements of the 20th century. He proved, with mathematical certainty, that in any formal logical system complex enough to include basic arithmetic,
Yes.
there will always be statements that are true, but that cannot be proven from within the system's own axioms.
I always have to pause and wrap my head around that. A statement can be true, but impossible to prove.
It means that no mathematical system can be both complete and consistent. There will always be truths that lie beyond its grasp. Math is not a closed, perfect loop. It has holes.
We have a note here that Stephen Hawking took this idea and applied it to physics. He suggested it might mean a theory of everything is impossible.
That was his argument. If a final theory of physics must be a finite set of mathematical equations, and Gödel proved that any such set of equations is necessarily incomplete, then it follows that physics itself might be endless. We might never be able to capture all of physical reality in a finite set of formulas.
There will always be another layer to the onion.
There could be. Now, other physicists disagree. They argue that physics isn't just pure math, it's about describing reality. And we don't need to prove every abstract theorem to know how an electron behaves. But it raises a fundamental question about the limits of our knowledge.
Which feels like the perfect setup for our final thought experiment. The alien question.
Ah, yes. Would aliens have the same math?
If math is truly universal, a discovered feature of the cosmos, then any intelligent species should eventually discover it.
You'd think so. A circle's ratio of circumference to diameter is pi, whether you're on Earth or on a planet orbiting Proxima Centauri. 2 plus 2 equals 4 everywhere. That seems non-negotiable.
But would they care about the same things? Would their mathematics look like ours? Would they use base 10? Would they develop something like calculus? Or would their brains be wired to understand motion and change in a completely different way we can't even imagine?
This gets back to Hamming's fishing net. Maybe their net is woven with a completely different pattern. Perhaps their physics is entirely stochastic, built on probability, and the idea of a deterministic law like ESMA would seem like a bizarrely simplistic fairy tale to them.
Maybe for them, the weirdness of the Banach-Tarski paradox isn't a paradox at all, but just
No.
how things work in their perception of reality.
It's possible. It raises the unsettling thought that our mathematics isn't the language of the universe, but just the language of the human brain. It's the operating system that runs best on our particular brand of biological hardware.
A compression algorithm for monkey brains.
And if that's true, we could be blind to entire swaths of reality that simply don't fit our compression format.
So as we wrap up, what's the final provocative thought you want to leave our listeners with?
I think it's this. We stand in awe of the unreasonable effectiveness of math because we see the models that succeeded. We see the bridge that stands, the vaccine that works, the spacecraft that lands.
But you see the survivors.
We see the survivors of a long, brutal Darwinian struggle for ideas. We don't see the thousands of failed models, the collapsed bridges, the ineffective formulas, the endless hunt for Vulcan. We remember Neptune, we forget Vulcan. Our perception of math's effectiveness is itself a product of selection bias.
So the final question for everyone listening is this. Is the power of math a miracle that reveals the deep structure of the universe? Or is it just a mirror reflecting the shape and the limits of our own minds?
That's the question.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content and support us in Patreon.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.
Have a great day.